part 2 of Symmetric Design 2. The first talk is entitled Impossibility of Indifferentiable Iterated Block Ciphers from 3 or less primitive calls. Joint work between Chun Guo, Lai Wang, and Dongdai Lin. Unfortunately, none of the speakers could be here, but fortunately, Yaobin Shen has been so kind to offer to present the work. Yaobin, take it away.
Yeah, that's the introduction. So I will be the proxy speaker of this talk. So let's begin with the background. So virtually all the modern block ciphers are iterative block ciphers. They usually a composition of small components, like a ROM function. So there are some two typical examples, like the facial cipher and also iterative master cipher. So the DES is the typical example of facial cipher, and the AES is also a typical example of iterative master cipher. So in this paper, we ask how many random permutation or function calls are necessary for a non-trivial iterated block cipher. So for the indistinguishable notion, we know that one call to a public permutation is enough to achieve the indistinguishability. So let's example the one wrong in master cipher. And how about the stronger notion in differentiability from ideal cipher? So in this model, the adversary not only to have access to the block cipher, but also to have access to the underlying primitive. Here is that part of P. So adversary want to distinguish the real world from the right part ideal world. There's the ideal cipher, and also the simulator try to simulate the underlying primitive. So why we consider the indifferentiability? Because of the composition theory. If the block cipher is indistinguishable from ideal cipher, then we can directly use to instantiate at construct C. Then the construct C will be secure, as secure as it is in this instantiate ideal cipher. But there are also some imitation, like a single stage or complexity broke up. Until now, we have very fruitful positive result, mostly for the block cipher like facial cipher, iterated in master cipher, and also diffusion networks. But we don't have general lower bounds. We only have some lower bound for a specific construction, like the key prepended facial cipher or iterated in master with key derivation, or iterated master without key derivations. So in this pair, let's go back to the question. So how many function or permutation calls are necessary for an non-trivial iterative block cipher in general sense? And let's begin with what does it mean by non-trivial. So an ideal cipher with ambiguous block is an exponential number of ambiguous random permutation. So if we already have exponentially number of the ambiguous permutation, then we already have ideal block cipher. So we will try to avoid the trivial case. So in this paper, we consider the oracle P that consists of multiple of permutations. And the permutation will have the wise size mi, and the size of mi will be the polynomial size. And we also divide the size into two sets. The one set is that the size of the permutation will be less than equals to the m-bit, and the other part will be larger than the m-bit. As mentioned, we will avoid the trivial case that the number of the m-bit permutation will be limited to just the polynomial size. But for the size that larger than the m-bit, we can have exponentially many large, because this offers indifferential functions and injections. Here is the notation that input is a tuple, I delta z, and the I delta is denote the index and also the direction. And z here is for input. So here is the contribution. So the main contribution of this paper is that we show that no iterative block cipher making 3 or less calls to the oracle P is statistically indifferentiable from ideal cipher. So this also implies that the 4-call result in previous paper is optimal. So here is the construction we consider in this paper. There are three types of construction. So the first one, the key derivation will takes two permutation core. So the main part of the block cipher will only have one permutation core. And the second type, the key derivation will have two permutation core, and the main part will only have one. We will have two permutation core. And the third is that the key derivation function does not take any permutation core, so the main part will have three permutation core. So let's look at the result in detail. So we first discuss for fundamental property of the block cipher. Let's have so from the definition of the block cipher, we know that block cipher should be efficient, invertible. So there will always a corresponding oracle procedure that compute is inverse. And the block cipher should also be deterministic. So evaluating the forward direction and backward direction always yield the same transcript of the oracle queries and response. And also by fix the description of oracle procedure, we know that the sub-procedure in this oracle in the EP are oracle independent. So we also know that long degeneracy, that no encipherment EP can be approximately computed using less P cost than the EP. So this is a fundamental property of the block cipher oracle. So let's begin with the first core cipher. So the top of the picture is the encryption of the one core block cipher, and the bottom is the decryption of this block cipher. So the adversary can have access on the middle part, there is the permutation. But for the left part and right part, it can only compute it, but cannot be accessed to the adversary because it involves the secret key. And this should also be inversible efficiently. So let's look at the fundamental property already includes a number of non-trivial properties. There are three properties like the inverse freeness and its oracle dependence, and also the property of the inverse free of the E1, and the property of the non-inverse free of E1 PKX. So for the inverse freeness and its oracle dependence, so it means that if the inverse free in cipher means that the forward of the block cipher and the backward of block cipher only invoke the same direction of the delta. So maybe only invoke the encryption of the permutation or the decryption of the permutation. So otherwise, the E1 is the non-inverse free. So we have an observation. So for the one core block cipher, the inverse freeness cannot depend on the oracle P, because if one can simply decide even in cipherman E1 is inverse free without querying the oracle P. And for the second property, there is inverse free. So if there's one inverse free of the E1, then it means there will be exponential number of the inverse. So let's look at the example of Facetail and Lyman-C. So they are always the 2 to the power half n distinct kx that will call the same functional call, because the part x is independent of the underlying function called f. So let's look more closely, so we can abstract the property of the Facetail or the image so in these two pictures. So if there exists an inverse free, then actually it can map to exponential many of encipherments. So, and this exponentially many encipherments also result in the 2 to the power n over the polynomial n possible points. And so also the property of non-inverse free, there is also a limitation that the size of permutation, the size of input cannot be larger than n bit, because if the size of input is larger than the n bit, then we need to have some padding, like padding with 0 or padding with the key. Then if we do the inverse of permutation, then this redundancy bit is analytically matched format. So the size of permutation should be less than n bit to achieve the long inverse free. So with the above property, we are able to bound into our differentiate a D1 on the one core block cipher. So in detail, the cipher may fall into two cases. So here's condition that we can only focus on the key size that is a bit larger than the polynomial. So for case A, so if there exists AD is one inverse free in cipherman, then as discussed, then it will be result in a exponential number of distinct inverse free with the same in cipherman. So the restriction of E1 to this domain is the bijection defined upon a polynomial length random string. Then we can use the entropy-based method to differentiable this from random injection functions. And for the case A, if the E1 is the long inverse free for all the key and the input, then by the pigeonhole principle, we can guarantee there always exists a pair with collision. Then using this collision, we can mount and take. And then we look into the two-code iterative block cipher. So there are only two types of this block cipher. The first type is that the key derivation only take count one permutation code. And the second type is the key derivation takes no permutation code. So in this case, we divide the key balance into two sets, the K0 and K1. And for the K1, it only invokes one called key derivation function. And for the K0, there's no key derivation function in the form of the Oracle procedures. And build upon our probe result on E1P, we can further consider our two-core model. So for the case 1, the E2 invokes the key derivation function for sufficiently many keys. Formally, the key size can be larger than the size of the permutation with less than bit. So we can simply pick a lambda keys and divide the subkey S1 and to the S lambda, and this consumes at most lambda p query. This is still polynomial. So we can then view the wrong pi3p as a one-core cipher with key space, and then apply our differentiator of the one-core block cipher. And the crucial point is that the D1 can break E1 with the polynomial key space. And for the case 2, it will be less obvious. So there will be always two iterations for most keys. So the overall framework is that our start point will be a boomerang property, and then using the graph theory, and then from the boomer to yo-yo, and then finally we'll use the long degenerate input function. So let's look step by step. So the starting point, we will use the boomerang property. So for example, in the two-round even muscle cipher, we can computing for distinct pairs, and they will introduce two collide input to the inverse of P1, and also the two collide input to the P2. And then we can compute the four tuple of cipher input outputs that has these four collisions. We will generalize to be a generalized boomerang and find four pairs that introduce a similar collided P-cos. So then we can compute four tuple of the cipher input outputs that has the these four collisions. But the problem is that there exists these four pairs, so that we can find these collisions. So for this one, we will regard this input-output pair as a graph, like a bipartite graph with left and right show size, which will be less than the 2 to the power n plus 1, and the key size multiplied by 2 to the over n. Then we find that there's already existing theory regarding the graph theory that is published in 2002 by Horry. It implies when the key size is super polynomial, then the cycle of length less than or equal to 4 must exist. But the problem is that since the key size is exponential 2 to the power n, we cannot simply invoke the attack for the E3 with the KDF. So we need to general yo-yo distinguisher. Then we consider longer cycles C2 lambda. So we need to find two lambda tuples and also certify these collisions. So then we can compute the two lambda tuple of E2 input-output pairs that has the cycle of collisions. Then we can again use this the Horace theory, and so then the key size is just a polynomial. And below above the result of E1P, we can further consider for the last step from the Boolean to UU, because there's also a point need to notice that the Hooray does not apply when G is the multigraph. But when the graph G is the multigraph, there's already exists a simple distinguisher. And a crucial point is to restrict our discussion only on the iterative block cipher with the clear weighted intermediate value set, because then the attacker can pick such a value and then compute the forward or backward. And for the attack on the three-core iterative block cipher, the idea will be similar, but will be more complicated. We need to discuss different cases. So then comes to a conclusion. So we propose a first general rule bound on indifferentiable block cipher. So informally, the non-iterative block cipher making 3 or less call to the Eurocrypt is statistically indifferentiable from ideal cipher. This also implies the previous 4-core result is optimal. And also our procedure is built on the Oracle list consists of many permutations. We also have shown the 4 fundamental property of block cipher Oracle procedures. And we also consider concrete model for a 1-core and 2-core, 3-core iterative block cipher. The attack idea is mainly using the invertibility and using the extremal graph theory. There are also some discussion in the paper. So actually, the inverse free run must admit some severe weakness regardless of its design. And also the wide permutation with width larger than n are not more helpful in constructing and build block ciphers. Also, we also support the popular construction like the iterative master cipher. There's no other choice can be better than this choice. And so also one of the reviewers suggests that permutation-based cryptography may be more efficient than ideal cipher, because to build an indifferential block cipher, we need to at least for permutation cost. But as usual, it is just work on the information theoretic security. There's some possible future construction that is extending our treatment for a fully general 2 or 3-core block ciphers. Or maybe smart idea to unify the complicated analysis in the E3 analysis, or concrete security to characterize the E2 or E3, or maybe other aspect memory restriction or adversary or achievable of computation in differentiability of the course, or maybe relaxing the conditions. Okay. Let's see. Thank you.
Thank you very much. So thank you, Xiaobin. As Xiaobin is not a co-author, please, if you have questions, send them by email to the authors. Thank you again. So now we move on to the second talk of the second part of Symmetric Design 2. So we have 3 times 2 and we have 3 authors. The paper is entitled Optimal Security for Keyed Hash Functions, Avoiding Time-Space Trade-offs for Finding Collisions. It's joint work between Cody Freitag, Harusht Koshal, and Ilan Komagotsky, and Ilan will give the talk.
Okay. Hi. Thanks for attending the talk. I'm Ilan. I'll talk about optimal security for keyed hash functions, avoiding time-space trade-offs for finding collisions. And this is based on joint work with Cody Freitag and Ashrajit Ghoshal. So we all know and love cryptographic hash functions, right? At least the API, I'll tell you how it works. The API receives as input, the primitive receives as input a huge arbitrary length input, possibly huge, and it outputs a fixed length digest that we will denote by X. So this is super useful, right? Any application that you can imagine will use somewhere a hash function. I'll just list the first four things that came to my mind, but there's many more applications. And if you think a little bit better about each application, you realize that most of them, you need a specific property of the hash function, specific security property. For instance, it could be collision resistance, second pre-image resistance, one-wayness, and so on. Some applications require the full random oracle assumption, but not all of them. So in this talk, I'll talk about specifically one property, only collision resistance. So this is the only property I'm going to care about in this talk. And this is central enough and useful enough property for many of the applications I listed. But if you read an introductory book in crypto, you know that collision resistance is only defined when you have a family of functions. Otherwise, it's only meaningful for uniform attackers. And we would like to understand the security of cryptographic hash functions against non-uniform attacks. So let's consider a family of hash functions. So now each function in my family accepts two inputs. One is the key, and the other is the input. The key is fixed length, and I'm assuming it's just n bits like the output for simplicity. And once you define the family this way, you can talk about collision resistance. You can say, OK, given a random key k, how long does it take me to find a collision with respect to this key? OK. And once we describe the task that we want to solve, we want to ask, OK, how do we solve it? How do we build this function h? So this is what happens in practice. People go and they design a single hash function that maps, for example, from 2n bits to n bits. So just accepts a fixed input length and outputs a fixed output length, which is shorter. And then they somehow iterate the construction and get a keyed family of hash functions, where each hash function in the family can support arbitrary length inputs. And probably the most well-known example of such iteration methods is Merkle-Damgard. You take a very long input, you split it into blocks that I denote by M1, M2, M3, and we feed them into H one by one, where the second input is the output of the previous application. The key k here is the key that defines the concrete hash function in the family. So this is a super basic construction, and this specific keyed version of Merkle-Damgard has been studied in many papers in the past years. So natural question, is this a good hash function? Is it collision resistant? Of course, before I tell you if this big thing is collision resistant, you need to tell me what is the small thing, what is h, small h. So we model small h as a random oracle, which is in particular collision resistant. But for the simplicity of the analysis, we say h is a completely random function. It goes from 2n bits to n bits. What can you tell me about the security of the big hash function? Is it collision resistant? So the model, the concrete model that we will be using to answer this question is called the Auxilliary-Input Random Oracle Model, or Al-ROM in short. It was introduced by Unruh about 15 years ago. And the model is very simple to describe. The adversary has two parts, A1 and A2. The A1 part is what we call the pre-processing phase or the offline phase. And this one has unbounded access to small h. It makes as many queries as it wants. It learns whatever it wants about h. And it outputs an S-bit advice. This advice goes into the online phase attacker that gets also the random key as input. And this guy makes T queries to H and needs to find a collision. If he succeeds, if A2 succeeds in finding a collision, we say that A1, A2 win the game. And notice that A1, A2, this attacker A, they're parameterized by two parameters, S and T. S is the size of the advice. T is the number of queries in the online phase. The security of a construction would be defined by the best possible attack, assuming that the first part has at most S bits of advice and the online phase can make at most T queries. Okay, so we understand the model. Let's see what the obvious attack is, or what we would like to hope for when we design this big H. Here's the trivial attack that any one of you would have thought about in 2 minutes. In the pre-processing phase, we just look for S collisions with respect to S different keys. So you just sample random keys, doesn't even matter how, and you just look for a collision with respect to each and one of them, and you output that as your advice. This is roughly S bits. In the online phase, what you do, you get the random key as challenge, you check if the key is one of the keys that you remembered in the offline phase. If so, you're happy, you have a collision stored in your advice. And if not, you just do a birthday style attack. You just try many different inputs until you hit a collision. This gives you an attack with advantage S over 2 power n plus T squared over 2 power n, where the S over 2 power n factor comes from the pre-processing phase, where you remember S collisions, and the T squared factor comes from the birthday attack. So this is an attack, and this is something that apparently is also achieved by a completely random construction. So a paper of Dodis, Guo, and Katz from 2017 showed that a completely random family of hash functions is secure up to this advantage. Namely, this is the best attack you can hope for if all of your functions in the family are random, completely random. But our functions are unfortunately not random. We do not know how to build a family of random functions. This is not how the world works. So a natural question is, what can we say about the security of existing constructions? So let's go back to the Merkle-Damgard example. So apparently, the Merkle-Damgard example is much less secure. A work by Coretti, Dodis, Guo, and Steinberger from 5 years ago showed an attack on Merkle-Damgard, on the kid version of Merkle-Damgard, with advantage S times T squared instead of S plus T squared. And this is really significant. If you plug in real numbers, it gives you a lot. So yeah, so there is a very non-trivial attack. This is also the best attack possible on this construction. But this leads us to, and there were a lot of follow-up works analyzing keyed Merkle-Damgard. This is not where it stopped. I won't tell you what they did. But it does lead us to the question of, is this the right construction to use for a keyed family? Is this multiplicative loss in S and T squared necessary? Can we achieve the baseline, or the thing that random functions give us? So this is the question that we ask and answer in this paper. We ask, what's the right way of taking a single fixed input length hash function and turn it into a family of a keyed family of hash functions that support variable input lengths? And is it even possible to achieve the baseline? Okay, so this is the baseline, just to remember. The security of Merkle-Damgard is S times T squared. And I'll give you a list of our constructions and what we achieve, but it will be more useful to compare them if we also take into account the efficiency of the construction. I'm going to measure the efficiency of the construction in terms of the number of calls that you make to your random oracle, the fixed random oracle H, when you process an input of m bits. Merkle-Damgard, if you remember, just splits the input into blocks of size n and feeds them one by one. So the efficiency of a Merkle-Damgard is m divided by n. Our first construction achieves optimal security. No security loss. It's just the best you can hope for. But it has somewhat terrible efficiency. The number of H calls that we have when we process a message of length m is roughly m. You can maybe shave off constants, but it's roughly m. So this is very bad. Our second construction, again, achieves optimal security, but now under the assumption that S is smaller than T. This is a significant assumption that limits the usefulness of this construction. But the efficiency of this construction is way, way, way better than the previous one. It's only twice less expensive than the insecure Merkle-Damgard. And our last construction, again, achieves optimal security, but now the assumption is much weaker on the relationship between S and T. We only assume ST squared is smaller than 2 power n. And the construction is somewhat efficient. It's only 3 times less efficient than Merkle-Damgard. We conjecture that the assumption in H3 is not necessary. It's just an artifact of our analysis. But the assumption in H2 is actually necessary. We have a matching attack. H1 and H2 mostly follow, once you understand the framework, mostly follow from known results. And most of our work is in the analysis of H3. Okay. I'm going to tell you the constructions in the rest of the talk. This is the first one. This is probably what you would have thought about when I gave you this problem. So this is just the plain Merkle-Damgard, as I described it before. But the change or the modification is that we feed the key not only to the first block, but to every block in the construction. This is somewhat obvious, and there are even places in the literature that define Merkle-Damgard in this way. The oldest source that I was able to find is the lecture notes of Gold, Vassel, and Belardo from 2008. This is actually how they define Merkle-Damgard. Without any apparent reason, they only analyze it in the uniform setting. But apparently this construction gives you optimal security in the non-uniform setting. And why? Let me give you a 2-sentence proof. It's a simple reduction. Assume that an adversary finds a collision with respect to this very long construction. Then, because it's a collision, there must be a collision in a single block also. You can reduce a very long collision to say, yeah, there is one block where the collision appeared, and from that point on, you just continued with the same path. And once you reduce it to the single block case, I just invoke the result of Doddy's, Guo, and Katz that showed that a single block construction is optimally secure. So this is the proof in 1 sentence. And as you can see, the number of H calls is terrible. It's roughly m, because we feed the key into each block, so we take away a lot of the message bits that we can feed. So that's construction 1. Construction 2, instead of feeding the 3 inputs to H, we construct a small keyed Merkle-Damgard, just a 2-block Merkle-Damgard, so the key goes into every block, but every block consists of 2 invocations of H, where the message goes into the second one, and the key and the previous output go to the first one. So this is the second construction. Obviously, this is twice less expensive than plain Merkle-Damgard, as you can see, because we replace every hash with 2 hashes, and we can, the rate of this construction is the same. So it's only twice less efficient. And we prove security under the assumption that S is smaller than T. How? Again, via a reduction to the case of 2-block Merkle-Damgard. So we say that if somebody finds a collision in this very long construction, we can actually find the collision in a keyed Merkle-Damgard with 2 blocks. And this was analyzed in Akshima, by a paper by Akshima, Cash, Drucker, and Wee 3 years ago. They proved that this construction is optimally secure, assuming that S is smaller than T. So this is the second construction. And now we move on to the third one, which is our final construction. So now, instead of doing a small Merkle-Damgard for every block, we build a small Merkle tree for every block. So the message and the key go into the first hash, the previous output along with the key go to the second hash, and then we combine both hashes with another hash. And this is the third construction. Obviously, it's 3 times less efficient than Merkle-Damgard, because we replace every hash function with 3 calls to a hash function. And the security proof here is really, really, really non-trivial. Again, we reduce the fact of finding a really long collision to an adversary that finds a collision with respect to a 1-level Merkle tree. And we analyze that using a recently introduced framework for analyzing time-space trade-off results. It's called the multi-instance framework. At a very high level, the multi-instance framework, what it allows us to do is to take a problem that we want to analyze in the ST model and sort of translate it into a completely uniform model where there's no S, but the game that we want to play is a game where the adversary needs to solve not just one instance, namely not find a single collision, but find many, 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 many collisions for many different instances. So because the adversary has lots of games to play, the analysis becomes a little bit harder, but at least we don't have the advice to take care of, so we can use existing tools like probability and compression arguments and things like that. So the proof here is a very elaborate and complicated case analysis that basically distinguishes between where the collision happened on which of these 3 H's and in which phase the adversary found those collisions. And this is the result that we managed to come up with. Again, the assumption, we believe the assumption is not necessary. We couldn't find attacks in any range of parameters, but this is what our proof resulted with. So that's the third construction. Let me just conclude. We gave a new way of building keyed hash function families from a single hash function. We used what I think is a very interesting and a new Merkle tree-based approach for building keyed hash functions. Prior works analyzed an existing construction, really took a hammer and proved everything possible about existing constructions, which are sort of weaker than what we proposed. And there are obvious open problems from this work. Prove the conjecture about the third construction, prove that it's optimal in all ranges of parameters, or find the corresponding attack. And come up with new constructions. I think this question didn't receive enough focus, and it should. So thank you so much for listening.
Thank you. It's time for questions. So, okay. Come to the microphone, please. Good. Evgeny.
Like a syntactic question, probably not this answer. Why do you put 0 in your last construction? Like one of the block has 0, you cannot squeeze a message there? Like there is a 0 to the end. If you put a message, you know,
Yeah,
like one of the block.
Yeah, you can.
Oh, but it's just one.
Yeah, you can.
I see. Well, but then, okay.
Just for the symmetry of the
right. Okay. But
of the drawing.
Less syntactic questions. So
yeah.
We get this paper about like T5, where you can actually insert a message in every block, like with XOR or something. It looks maybe it's like a mess already without. Doesn't work, or it's.
I don't know how to prove it. We tried.
But that would be 2 certs. Okay.
Yeah. It's a great question. We tried, we couldn't prove it. This was already complicated enough. Your construction is even more elaborate. Yeah. There's more calls to H and more combinatorial steps. Yeah, this was already complicated enough.
Cool, yeah, nice.
Okay, let's ask an easy question. So for your other construction, you have S less than T.
for the second construction.
But in
right.
practice, I mean, if you have to store the output, say if S is to the 60, it's very hard to store. Well, to the 60 computations is kind of easy. So maybe this is already good enough, S less than T. Or what's your view on this?
Yeah, so every setting of parameters is useful for a different application. Of course, if S is smaller than T, that might suffice. Yeah, you're right. There are applications where S is smaller than T makes sense, and there are applications where the opposite makes sense.
Okay, there's no further questions. Let's thank Ilan and also Jaubin, the other speaker of this session. Thank you very much. So we finished right on time. You now have the right to your coffee break for 30 minutes. And next up in this room will be, you guessed it, Symmetric Design 3.